Hello everyone, thank you for being here. Today we'll talk about learning to rearrange deformable cable, fabric, and bag with goal condition transporter networks. There's been a lot of significant recent progress in robot learning for manipulation with applications including bin picking, tossing item, reorienting a cube. While these results are very impressive, an assumption that these methods make, implicitly or explicitly, is that the items being manipulated are rigid or almost rigid instead of highly deformable. Manipulation of deformable objects has many applications, including handling towels and laundry, bed making, wrapping items, and so on. But in contrast to rigid object manipulation, deformable object manipulation has several challenges. First, how do we represent the state of an object? If we have a rigid block, for example, it's enough to know the position and orientation of a fixed point on the block for us to determine the block's overall arrangement in three-dimensional space. In contrast, with a t-shirt, for example, a robot could be fixing points on the t-shirt, but the other points away from the grippers could vary a lot. Furthermore, there's also challenges in designing a policy on top of this because of difficulty with using planning methods, since many planning methods require knowledge of, given the current state in action, what is the next state going to look like? Nonetheless, the robotic community has done a fair amount of prior work in manipulating deformable with applications like tying and untying knots, folding towels and laundry, smoothing slightly wrinkled fabric, and robot bed making. More recently, there's also been a lot of focus on learning how to manipulate deformable by first training in simulation and then transferring the policies to the real world with potentially fine-tuning if needed. While the results are all very impressive, it's difficult to benchmark progress in the robotics community because even when roboticists are focusing on the same tasks like smoothing, they might use different robots, different fabric, different action spaces. So it raises the need of a standardized sort of benchmark for being able to measure progress. That brings us to the current work. In this work, we have two main contributions. The first is a suite of 12 simulated tasks in PyBullet that span cable, fabrics, and bag. So PyBullet is a very common and widely used physics simulator for robotics research. And we propose this benchmark of tasks, which is open source, so that other researchers can try out their own algorithms and ideas on it, so that we can better benchmark progress in deformable object manipulation research. The other main contribution of this work are a set of model architecture for manipulating objects toward desired goal configuration specified with images. And I also want to highlight here that this is well suited for deformable because given a desired goal configuration for deformable, it may be difficult to specify this with a series of poses. All the tasks in the suite come with a standardized setup with a UR5 robot arm and a workspace of objects in front of it. All the tasks also come with a scripted demonstrator that shows how to perform the task with a sequence of pick-and-place action. Different tasks convey the success criteria in different ways. So, for example, this task here, when visualized with a top-down camera view of the workspace, shows a cable that must be aligned with the green target zone. Given this, the robot must perform a sequence of pick-and-place action to get the cable to be aligned with the target zone, which it does sequentially, action by action, by trying to correct for the largest discrepancy between the current cable and the target zone. In this case, after 5 actions, it successfully gets to the target, and the demonstration data that would be provided to a learning-based algorithm would consist of 5 pairs of images and action. Other tasks are what we call goal conditions, such as the one shown here, in that given the current image, the robot must be given a separate goal image fixed for each demonstration that shows how to perform the task. So in this case, again, it's very similar to the prior one, except we use a held out image to specify where the success criteria should be. So given this, again, the robot takes a sequence of pick and place action to try to get the current cable to match within the target goal image, which is fixed throughout the episode. And I want to highlight here that if the goal image were different, but the configuration of the cable at the beginning was the same, then the robot would have a different success criteria. At this point, the data provided to a learning-based algorithm would consist of an image, an action, and a goal image at each time step. We also have tasks that have fabric. These include wrapping item or smoothing fabric, where the smoothing can be towards a target zone specified on the workspace or target zone specified with a held out goal image in the goal condition variant. So in this case, for example, given the goal image, the demonstrator takes a sequence of pick and place action on the fabric corner in order to get the fabric to be aligned with what is conveyed in the goal image. Finally, the most interesting case is with bags. So bags have a very obvious application and motivation in robotics, because if we can get robots to manipulate bags very well, then it can insert and then transport many items simultaneously rather than moving those items one by one. But we've also seen very little prior work in robots manipulating bags because of complexities in simulation and manipulation. So the task that use bags in the suite involve opening up the bag if necessary, inserting one or two items in it, and then putting it into a target zone if necessary. In the goal condition variant that we have, given the goal image which has the bag that contained an item, the robot must infer that the first action should be, if necessary, to open up the bag that is to contain the target item. In this case, it's the red bag. Then the second action should put the item in the red bag instead of the distractor cyan bag. If the goal image instead had the item in the cyan bag, then the robot would have to put it in that bag instead of the red one. Alright, next we move to the model architecture portion of this work, where we discuss the model architectures that we use in combination with demonstration to address the task we just discussed. The model architecture that we use is based on something called transporter network, a recent innovation presented at Coral last year. So we'll briefly review what transporter networks does, and then we'll discuss what we did. So transporter networks are very well suited for rearrangement. They consist of two main steps. The first is to localize the region of interest, and then to infer spatial displacement, where the localized region can encompass the entire object of interest, part of the object, or multiple objects. Transporter network does not predict two continuous control values. Instead, it takes deep visual features and performs a brute force search over the underlying image to get a correlation map, where the highest value indicates the displacement spot. This is conceptually what a convolution operator does, and so we can efficiently implement this on a GPU. Taking a broader step back, this is the overall architecture for a transporter network for a hypothetical picking and placing task. The main thing to highlight here is that the transport operation happens at the very end when it does the convolution operator, and the things that it operates on are not the original image or the original crop image, but are instead deep features that are output of fully convolutional neural networks, which in this case are 43-layer residual networks. So all that was prior work, and here's what we did. We brought goal conditioning into transporter network. That means in addition to a current image, we have to somehow process a goal image. So here's how the control flow works. So the current image will be passed into 3 fully convolutional neural networks. They all have the same architecture. So this is basically similar to what vanilla transporters does. They pass the current image into a picking network to determine which spot the robot should be picking at, in addition to 2 other networks which we call query logic and key logic. Again, these are just producing deep visual features. What's new here is that we have a goal image. In order to make use of the goal image, we have to process it into the network somehow. So the first thing we do is we pass it to the picking network again, so that the picking network uses the goal information into account when I determine which area to pick at. But we also have a separate goal network that produces goal features. So, given all of this, we then have to somehow combine the information to determine the placing point. But in order to do this, we need to have information from the goal image, otherwise we're not using it. So the way that we use it is before the transport operation, we combine the goal logic with both query and key logic with element-wise multiplication. At this point, we now have what we call goal time query features and goal time key features. These now have information about the goal image taken into account. And therefore, we can then do what the normal transporter does by taking a crop at the picking point and then doing a convolution operator to determine a placing heat map, where the highest score indicates the placing spot. And furthermore, where the entire network is trained end-to-end through backpropagation from demonstration with behavior cloning. Here are some examples of the learned transporter networks in action. And we see that qualitatively, the robot is able to effectively open up the bag, insert 1 or 2 items in the bag, and then to pick and pull at the bag so that it goes upward and then drops into the target zone. We also have results with the goal condition variant of transporter networks, where given the goal image that shows the block in the yellow bag, the robot at test time sees that it must be able to put the block in that bag instead of the distractor blue bag. Quantitatively, we benchmark results on all 12 of the tasks in the suite, where 8 of them do not have goal conditioning and 4 of them are considered goal conditioned. We benchmark the transporter networks-based approach with methods that use ground truth, vertex, and post information so that they don't use images as input, but the ground truth poses and vertex information. We find that when we look at success rate as a function of 1, 10, 100, and 1,000 demonstration for training the policy, the transporter network approach is orders of magnitude more sample efficient than the alternative. But the result did not come without limitations. So one example of a limitation is with the coarse pick and place action formulation that we use. So given the situation, the robot pulls the bag upward, but the item falls out. So the robot cannot perform recovery policies. In conclusion, we propose an open source benchmark for deformable manipulation and a goal condition extension of transporter network, along with learned policy for deformable manipulation. In future work, the top priority is to extend this to physical bagging, as well as to test by manual manipulation and going beyond pick and place action. The project website and code are available online. We hope you enjoy it, and thank you for watching.